k-means is one of the simplest approaches to clustering. And in clustering is a unsupervised problem in which we are given some data x1 through xn. And let's draw a picture over here to sort of visualize what's going on. So we've got maybe just some axes here, and we've got some points. So I'll just draw the points in our data set. Say maybe there's something sort of like this. And I'll draw them somewhat suggestively, perhaps. Something like that, maybe. And the task in clustering is to identify groups of data points and assign each point to one of those groups. So here I drew it sort of to suggest that perhaps there would be 3 groups. Something like this, maybe. Maybe something like this. Well, I guess they all have to belong to some group. Maybe that one belongs to here also. But you may be wondering to yourself, well, okay, that's fine, but what is a good clustering? And that's a very good question. And in fact, there's no universal agreement on what makes a good clustering. But in this video, we'll talk about one approach, which is the k-means approach to clustering. And in k-means, the intuition is that there are certain points which are the centers of the clusters, and maybe these are sort of the centers. And each point in the cluster is nearer to the center of that cluster than it is to the center of another cluster. So points are nearer to the center, quote unquote, of their cluster. So this is just sort of a guiding intuition. And let's start to make this a little more precise. So that's one problem, right? One problem is, what is the concept of a cluster? And another problem is, how many clusters should we look for? You know, you might want to let the data tell you how many clusters there are. But in k-means, it turns out that we're going to pick a certain number of clusters ahead of time, k, and we will look for that many clusters. So we will assume, in k-means, assume capital K clusters with centers. I'll call them centers for now. So each cluster has a center, and let's call the centers mu1 to mu_k. And let's consider the case of, in general in clustering, you may consider these points to just be d-dimensional vectors in some space, maybe not real space. But in k-means, we're going to consider them to be d-dimensional. So down here, the centers should live in the same space as the points themselves, and so these are going to be d-dimensional real vectors. And now let's formalize this intuition a little bit here. So let's think about the sum. So what does this mean? Sort of, the points are nearer to the center of their cluster. So that sort of tells us that we should assign points to the nearest center, but what should the centers be? We have to decide not only what the assignments are, what the assignment of each point to a center, but also what the centers are. So let's write down, let's say we have some centers here. We don't know what these are, so I should say with unknown centers. So one measure of how good a clustering is would be sort of the sum of the distances to the center. So let's think about, for this one, say maybe this is center 1, or cluster 1, cluster 2, and cluster 3. So for cluster 1, we would have the sum of the distance. The distance is just the Euclidean distance, xi minus mu j, well, so in j would be 1. And let's take the squared Euclidean. Let's take the sum of the squares of the Euclidean distance. That's what we do in k-means. And we would sum this over all points I such that xi is assigned to mu j. Or I might just say I is assigned to j. That's the sum of all these, the squares of all these distances here. And then we should sum that over all the different clusters. So we'll sum over j from 1 to k. We have k clusters. Let me put actually xi. That's maybe a little clearer here. Keep that as xi. So we sum over all the clusters the sum of the squares of the distances to the center of that cluster. Let's give this thing a name. This is a L. This is some quantity L, which depends on, so the x's are fixed, but it depends on mu and these assignments. And let's rewrite this in a little bit different way. Let's instead sum, so we could change this to be the sum over j from 1 to k, and instead sum over all the points I from 1 to n, and put a coefficient here that's either 0 or 1, depending on whether it's assigned to j. xi minus mu j. And here, aij equals 1 if xi is assigned to j, to mu j, and 0 otherwise, 0 else assigned. Right, and that's just exactly, so this is then just equal to this. Now the k-means algorithm, so that's sort of the setup. So the k-means algorithm says, okay, so this is the thing that we are trying to minimize here. We're trying to minimize this L quantity. So we want to choose mu's and a's to minimize this. But it's difficult to minimize this analytically. I mean, you can't minimize it analytically because these a's are sort of this sort of binary thing that's going on here. These assignments, these hard sort of assignments, make it difficult to analytically, or impossible to analytically minimize this. But what the k-means algorithm does is tries to iteratively solve this. So k-means does the following. Try to minimize L with respect to A, by this I mean just all the A's and all the mu's, by the following. First, so we're going to alternate between two steps, A and B. First, we're going to choose the optimal assignments A for let's say, fixed centers mu. So we'll first, so maybe there's sort of an initialization step here. So initialize, I should say, step 0 is initialize mu 1 through mu k. Just choose them sort of arbitrarily. There's other ways to, certain algorithms, certain variations of k-means choose these in different ways. But let's say for now, just choose them all to just be maybe random points, or random distinct points from the data set. So the first step is choose the optimal assignment for fixed mu. So we have these mu's. We choose the optimal assignments, whatever that turns out to be. We'll come back to figure that out. And then B, choose the optimal mu. It's supposed to be a mu for fixed A. So the first step is, in this iteration, is we fix mu, optimize A. The second step is fix A, optimize mu. And then repeat. So iteratively repeat A and B until convergence. Until things stop changing. So this is sort of a greedy sort of algorithm. And it turns out, so we're going to come, in just a sec, we're going to figure out what exactly steps A and B are. But let me just make a brief comment that it turns out that k-means, this sort of alternating minimization, is essentially a special case of the EM algorithm, or the expectation maximization algorithm, in which you try to find an MLE or map estimate of parameters. And so we're going to talk about that connection a little bit more in future videos. So how do we do this? How do we do A and B here? So A, the optimal choice of assignments, well, let's think about the picture here. The optimal choice of assignments for a given point, if we fix these centers, then we want to assign each point to the nearest center. That's pretty clear. If you didn't, so if the optimal assignment did not assign a given point to the nearest center, like maybe this one here, maybe this one was assigned to 3, and that was not nearest, then you could always reduce this L function by assigning it to the nearest one, which is 2. So therefore, we should always assign, in step A, assign each point xi to the nearest mu, i.e., we will choose aij to be 1 if j equals the minimizer over all L of the distance from xi to mu L squared. Minimizing the Euclidean distance is the same as minimizing its square, and 0 otherwise. Okay. So that's good for A. That's simple enough. And what about B? So B, it turns out, it's easy to differentiate this thing. And I won't go through it now, but it's a very sort of simple exercise for you to do, to work out, if you're interested. To work out, if you minimize this with respect to each of the coordinates of each of these mu's, what you get is you choose mu j to be 1 over, well, I'll put it in terms of the a's. Well, maybe I should do it. Maybe I'll do it. Maybe I'll pause. Maybe I'll stop in this video for now, and we'll go through this calculation fully. It's not hard. It's so maybe it'd be good to actually see that as an example of how to do this kind of thing. So let me stop there, and then we'll do this calculation and get the part B in the next video.